Our next chapter is all about counting. And really, when you're counting things, something that comes up all the time is factorial notation. Now, you might have seen it before. It's where we have a number followed by an exclamation mark. Now, what this exclamation mark means is an operation. It means take that number that you've started with and multiply it by a number that's one smaller, and then multiply that by a number that's one smaller again, and one smaller again, and one smaller again. So, for example, 5 factorial would be 5 times 4 times 3 times 2 times 1. And we can work that out and see that that's 120. Now, you can work your factorials out using your calculator if you want to. So, for example, 5 factorial, you just press the 5, and then your factorial button is X with an exclamation mark in that top right-hand corner there. Press that and hit equals, and it should come up with 120. You'll also notice that when we're working with factorials, because we need to take 1 off the starting number each time, we're working with integers here. Now, informally, if we came up with a kind of a recipe or a formula for what this exclamation mark really means, we could say that n factorial means start with n and then multiply it by a number that's one smaller, n minus 1. Multiply that by n minus 2, and so on, until you're down all the way to these numbers 3, 2, 1, because that's where we finish. We don't go into negative numbers. Now, we call this an informal definition for n factorial because it tells us what to do, but it's not a really great definition. It's not the one that we want to put our box around and memorize. Why not? Well, it's got a few problems. For example, what if you were figuring out 2 factorial and you started with this recipe, and then straight away you'd be down to 0, and then you'd be thinking, hold on, do I need to go to 3, 2, 1? You'd be a little bit confused. So it's not going to work for a really small number. The other problem with it is it's got these dots in the middle of it, which is okay as a concept, but we can do better. So looking at a formal definition now for the same thing, what we can say, just to really simplify this, is that n factorial is actually just n multiplied by n minus 1 factorial. Now, this keeps it really simple because effectively this second part is a factorial in its own right. So then to work it out, you'd say n minus 1 factorial is n minus 1 multiplied by n minus 2 factorial, and you could go on and on. Now, there's a couple of important things to note here. This formula will work for any values of n that are greater than or equal to 1. So if you had 1 factorial here, you'd have 1 multiplied by 0 factorial. Now you can see that there's a problem here. If it works for all n greater than or equal to 1, we need to know what 0 factorial is. For now, I'll give away that it's 1, and I'll prove it to you in just a moment so that you can understand that properly. Now, this formal definition of n factorial, it's a recursive formula, and that means it relies on something recurring over and over again. It really just gives the first step, but that first step in itself gives you the second step, and so on and so on. It also avoids the use of the dots. It works for all values of n greater than or equal to 1. And most importantly, this definition really helps us to manipulate factorials because we're basically unrolling them. And that helps us when we're simplifying fractions or any other expressions that have got factorials in them, as you'll see in a moment. So we need to understand this 0 factorial and why it equals 1. And we need to work out how to manipulate these factorials by unrolling them. Now, to understand why 0 factorial would equal 1, we can use 2 sort of strategies. The first one says, well, let's just look at patterns. If we use the informal definition to come up with some factorials that we can clearly and easily write out, then we can work out the answers to these quite simply. And we can see that 1 factorial is just 1. But the formal definition actually says, look, n factorial is n multiplied by a number that's 1 smaller than n with a factorial on it. And that means that 1 factorial by rights should be 1 multiplied by 0 factorial. Now, that's the formal definition. And for that formal definition to work, it also makes sense to say, well, hold on a minute, we already know what 1 factorial is. It's 1. So if 1 is also equal to this, 1 multiplied by something, then that something must also be 1. Does that make sense? So that use of the formal definition actually pretty much defines what 0 factorial has to be to make this true. Now, this second method of understanding it says, well, let's just think back to what the empty sum would be, and then we can think about what an empty product would be. Now, if you are ready to add some things and you're thinking, all right, tell me what to add and I'll add it to my register, I'll add it up. Then if you haven't added anything to anything else yet, your register is pretty much beginning at 0, isn't it? Because you haven't added anything to anything else yet, so your starting point is 0. Well, an empty product is when you're getting ready to multiply something by something else, but you haven't put any numbers into those two places yet. And so your register effectively starts at 1. Now, why does it start at 1? Well, the simplest thing that you can multiply, really, and remember that multiplying, we're saying how many lots of a number have I got here? Well, the simplest thing you could have is one lot of something. So if I tell you I've got two numbers and I'm going to multiply them together, but I only actually tell you what one of the numbers is, it's reasonable to assume that our register is starting with one lot of that number. So if I haven't given you any numbers to put in yet, it's also reasonable to say we've got one lot of something. We're waiting to see what. And so that gives us the whole concept that the empty product begins at 1. And here, when we're looking at 0 factorial, it literally is an empty product because it's some things multiplied, but there's nothing in there yet. And so we effectively start with 1. Now let's look at how we can unroll factorials. Now this is quite simple. All you need to do is remember that, for example, 8 factorial is actually 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So we can use our formal definition to unroll this once by just saying, look, it's 8 times 7 factorial. But then we know that 7 factorial is actually 7 times 6 factorial. So if we unroll it again, we can actually roll it out like this. But then we know that 6 factorial is also 6 multiplied by 5 factorial. We can go on and on with this all the way down, either unrolling once, twice, 3 times, as many times as we need to. Now, why do we want to do this? Well, it helps us basically just to simplify any fractions that have got factorials in them, and you'll see that in a moment. Now, the time that you're most likely to get a little bit mixed up is when you're dealing with, instead of integers, some sort of expression that has a factorial on it. So bear in mind that if you've added to a number, you've made it bigger, and if you've subtracted an integer, then you've made it smaller. So if you're starting with something like n plus 2 factorial and you want to unroll it once, then you've got n plus 2 multiplied by a number that's 1 smaller than that, which is, of course, n plus 2 minus 1, which is just n plus 1 factorial. And then if you unroll it a second time, you'll see that instead of n plus 1, you'll just get n factorial. And when that gets 1 smaller, you'll be into n minus 1 and then n minus 2 and so on, depending on how many times you want to unroll it. If you're working with something that starts off being smaller than a pronumeral, for example, k minus 1, then bear in mind that the next number, the lower than k minus 1, is k minus 1 minus 1, which is k minus 2 factorial. And so unrolling that a number of times will give you this sort of pattern. Now you might notice that I've written my terms out here with multiplication signs in between them. And strictly when we're writing algebra, we don't need to do that. One reason that I've done it though is when you're learning, it's quite helpful to think of these as separate terms and to keep them in their brackets, just to keep them separate. I mean, strictly they're not required, and we could just smush these two together here and write it like that. But one thing we want to be careful of is that we don't want to confuse this as a big expression like that has the factorial on the whole thing. We want to make sure it's really obvious that the factorial is only being applied to this number here. So I think that using the times signs when you're learning probably helps you just to keep things really straight in your mind. Now a couple of examples showing you why and when you would unroll factorials. Now we've already seen that you can put this into your calculator, but we need to have a method that works even when we're dealing with pronumerals. So it makes sense to look at the longhand way. So here, there's a line of working that we'll do when we're learning, but when you get good at this, you'll be able to leave out. We can express 6 factorial in terms of 4 factorial, because we know that 6 factorial, if we unroll it twice, is actually 6 times 5 times 4 times 3 times 2 times 1, which is just 4 factorial. So if we rewrite the top like that and keep the bottom the same, we can clearly see now that we can cancel the 4 factorial, and all that we're left with is 6 5s, and so the answer is 30. Now, once you get good at doing this, you might be able to work out that the answer to that is 30 much quicker than you can actually type the whole thing into your calculator. But as I said, knowing how to do it longhand is going to help you when you've got one with nasty pronumerals in it, because you can see what to do. All right, in this second example, we need to subtract fractions. And rather than punching this into our calculator, let's look how to do it longhand. Now, we want to make common denominators. So effectively, we're looking for a common denominator that they can both share. Well, it's easier to make a denominator that's bigger. So this one needs to be made bigger. We can actually rewrite the question so that they are both containing a denominator of 10 factorial. This one we've kept the same. This one we've done something to the denominator. We've multiplied this number by 10 and we've multiplied it by 9. Because don't forget that 10 factorial, this is what you'll be thinking in your head, is 10 times 9 times 8 factorial. So effectively, to turn this into this, we've just had to multiply it by 90. So if we've multiplied the denominator by 90, we can multiply the numerator by 90 and we get this. Now we can go ahead and perform the subtraction. Our denominator stays the same and 90 minus 1 is 89. Now again, you could punch this into your calculator, but if you're dealing with one with pronumerals, you'll need to know how to do this unrolling method. So here's an example that forces us to know how to do this. Firstly, looking at the two numbers, work out which one is the bigger one, because we want to unroll the bigger number. So this one's clearly the bigger one, n plus 2 compared with n minus 1. So I want to unroll the top until I get it in terms of the bottom. So let's do this part here. We'll say it's n plus 2. I might leave out my times signs this time because it's going to make my expression just a little bit simpler. I can multiply it by a number 1 smaller, then by a number 1 smaller than that, and then by a number 1 smaller than that. And wherever I like, I can stop unrolling and just put my exclamation mark on. So I'm going to stop here because that part there is now the same as my denominator. So I've unrolled the numerator 3 times, and now I can see that I can cancel these parts. And so the answer, I can write it in any order really, but let's just keep it the same, is going to be this.